VOLTAIC cells, also known as galvanic cells. A VOLTAIC cell is a device used to produce electric energy from an oxidation-reduction reaction. And if we remember a redox reaction, we're looking at two half reactions, one in which electrons are being lost and one in which electrons are being gained. And the way that a VOLTAIC cell works is that the oxidation half reaction will be separated into one compartment. The reduction half reaction will be separated into a different compartment, and then the two compartments will be connected by a wire. In the one compartment, the oxidation half reaction is going to take place, and electrons are going to be generated. They're going to flow to the other compartment where the reduction half reaction is going to take place. And the flow of electrons is what produces an electric current. We're going to call the compartment where the oxidation half reaction takes place the anode compartment. And the compartment where the reduction half reaction takes place is referred to as the cathode compartment. Sometimes VOLTAIC cells are written in a shorthand method. And in this case, the oxidation half reaction is written first. The reduction half reaction is then written second. And the two half reactions are separated by two vertical lines, and those vertical lines represent a salt bridge. So what we're going to do now is draw a very general diagram of a VOLTAIC cell. So the first thing we're going to do is draw our two compartments. And there's lots of different ways that these compartments can be arranged. We're going to use them as two beakers. We're going to put the anode compartment on the left-hand side and the cathode compartment on the right-hand side. And remember that the oxidation half reaction is going to take place in the anode, and the reduction half reaction is going to take place in the cathode. And traditionally, when we look at VOLTAIC cells, what we have are two solutions that contain ions, and they typically have two metal strips submerged in those solutions. And the atoms in the metal strip are the same as the ions that are found in the solution. The two metal strips are connected by a wire which allows electrons to flow. And there's a VOLTAIC cell or a voltmeter which allows us to measure the voltage. The electrons are generated at the anode and are going to be consumed at the cathode, so the electrons are going to be flowing from the anode to the cathode, and that's alphabetical. Now the electrons are going to build up on the cathode side and eventually stop flowing unless there's something to keep the system neutral. And that's called a salt bridge. And there's lots of different ways that salt bridges can be arranged. Often they're hollow glass tubes filled with a resin that only allows ions to flow. The ions, negative ions, would flow in the opposite direction of the electron flow, and therefore keeping the system neutral. Next, we need to talk about standard cell potentials. A standard cell potential is the measured cell potential when the ion concentrations in the half cells are 1 molar and at 25 degrees Celsius and 101 kilopascals. And the standard cell potentials are what are going to enable us to calculate the voltage across the cell. And the way we're going to calculate that voltage is by taking the standard reduction potential value for the reduction half reaction and subtracting the standard reduction potential for the oxidation half reaction. And these values are read off a table. So what you want to do is get your textbook, and again we're going to reference a table in the appendix, and the table we're going to reference this time is on page A25. So if we look at Appendix A25, we see a table of standard reduction potentials at 25 degrees Celsius. And we're going to notice that all of the half reactions in this table are written as reduction half reactions. And the table is arranged from the most likely to be reduced to the least likely to be reduced, or the most likely to gain electrons to the least likely to gain electrons. And if we think about that, the table makes sense. If we look at the first thing listed on the table, we're looking at fluorine becoming fluoride ions. And we know from our study of electronegativities that fluorine is the most electronegative element on the whole periodic table. So it makes sense that it would have the highest standard reduction potential and would be the most likely to be reduced in a redox reaction. If we look all the way down in the lower right-hand corner of the table, we're going to see lithium ions becoming lithium atoms. And we know that it's not likely that lithium ions are going to become lithium atoms because they're metals. They tend to lose electrons and become positively charged ions. So when we look at the standard reduction potential for lithium ions, we see that it's got the most negative value on the whole table. The more positive the value on the table, the more likely it is to be reduced. The more negative the value is, the more likely it is to be oxidized. So we're going to calculate a standard cell potential and draw a VOLTAIC cell. And we're going to use this as our example. A VOLTAIC cell is constructed using the following half reactions. So we're told that in one compartment we're going to have iron 3 ions going to iron 2 ions, and in our second compartment we've got nickel ions going to nickel atoms. And what we're going to have to do first is use our table to determine which one of those half reactions is going to be the reduction half reaction and which one's going to be the oxidation half reaction. And once we do that, we're going to be able to calculate the voltage across the cell and draw our VOLTAIC cell. So we're going to determine the cell reaction and calculate the standard cell potential. So first we're going to look the values up on the table, and you need to be very careful because especially for the iron 3 to iron 2, there are a couple of different half reactions on the table that talk about iron. You want to make sure that you use the right one. So I'm going to give you a minute, find the value for iron 3 ions being reduced to iron 2 ions, and nickel ions being reduced to nickel atoms, and see what you get for your value. So the standard reduction potential value for iron 3 ions to iron 2 ions is positive 0.771, and the standard reduction potential for nickel atoms going to nickel, or nickel ions going to nickel atoms, is negative 0.257. So what we're going to do next is we're going to decide which one of those half reactions is the reduction and which one's the oxidation. Remember that the half cell with the more positive reduction potential is the one in which the reduction occurs. And remember again that reduction takes place at the cathode. Once we do that, we know that the other half reaction is going to have to be the oxidation half reaction. And remember that the oxidation half reaction takes place at the anode. The next thing we're going to do is we're going to add the two half reactions together. But remember, from balancing redox reactions, we need to make sure that the electrons lost equal the electrons gained. And then once we do that, we can calculate the standard cell potential by taking the standard reduction potential for the reduction half reaction and subtracting the standard reduction potential for the oxidation half reaction. So by looking at the values on the table, we're going to decide that the nickel is the one that's going to be oxidized because it's got the smaller standard reduction potential. So that means our iron 3 ions are the ones that are going to be reduced. So now we're going to want to add our two half reactions together to get our overall reaction for this redox reaction. But when we notice there are 2 electrons being lost in the oxidation and only 1 electron being gained in the reduction. So we're going to have to multiply the reduction half reaction by 2, so the electrons gained equal the electrons lost. And what we're left with is 1 nickel atom plus 2 iron 3 ions for every 1 nickel ion and 2 iron 2 ions. Now we want to calculate the reduction potential. So we're going to take the standard reduction potential for the reduction minus the standard reduction potential for the oxidation, and that will give us our value. So we'll plug in positive 0.771 for the standard reduction potential for our iron 3, and we'll plug in negative 0.257 for the standard reduction potential for our nickel. And when we subtract our oxidation from our reduction value, we're going to get a positive 1.028. And in order for us to do this problem correctly, we should get a positive E0 cell every time. If we calculate that value and it comes up negative, it means that we switched the oxidation and reduction reactions around. The other thing we need to notice is that even though we multiplied the reduction half reaction by 2 to balance the equation, we're not multiplying the equation, or we're not multiplying the standard reduction potential. Now let's draw our VOLTAIC cell. So we'll have our 2 compartments. We know that we're going to put our anode compartment on the left and our cathode compartment on the right. We know that the oxidation half reaction takes place in the anode. So for this particular example, nickel atoms are going to become nickel ions, and we're going to release 2 electrons. We know that reduction takes place at our cathode, and in this case, we've got iron 3 ions that are gaining electrons to become iron 2. So what we're going to have is a solution in our anode compartment that contains nickel ions and some negative ion, maybe nitrate. And we've got a piece of nickel metal submerged in that nickel ion solution. Now over in our cathode compartment, we have something a little unusual because we have both ions in our reduction half reaction. So we're going to have a mixture of iron 3 ions and iron 2 ions in that solution. So what would have to be added to this particular one is a piece of metal that's going to allow the electrons to flow into the cathode compartment, and oftentimes that piece of metal is made out of platinum. It's not part of the reaction, but it allows the electrons to flow into the cathode compartment. We're going to connect the 2 half reactions together with some metal, and we're going to attach it to a voltmeter so we can measure the voltage. But electrons aren't going to flow just yet because we need to have something that keeps the system neutral. So we would have that salt bridge, which allows the ions to flow in the opposite direction of the electrons. So the electrons are going to flow from the anode compartment to the cathode compartment. The voltmeter is going to register 1.028 volts. And we're going to notice that the amount of nickel on that nickel electrode is going to go down, and the concentration of nickel ions is going to go up over time. Over in the cathode compartment, we're going to notice that the concentration of iron 3 ions is going to go down, while the concentration of iron 2 ions goes up over time. And what we're doing here again is we're taking a redox reaction and we're producing an electric current. So we're looking at electrochemistry, where electricity is generated from a chemical reaction.